I'm going to be talking about robots, but mostly how they're used for disasters, which is a great use of robots for society and AI. But at first, I want to just mention that we have a new NSF AI Institute for Societal Decision Making, so basic research in societal and decision making, but the societal aspect is our two use cases are disasters and public health. So that's similar and different, and we welcome collaboration. So I think you probably know what this talk is going to be about, right? That advances in legged and humanoid robots are going to revolutionize search and rescue. That computer vision, machine learning, it's mature, it works, it's great. We're going to transition that. You're going to see those transitions. And that regulations and doctrine will really help ensure that disaster robots are used safely and wisely. This isn't that talk. What I will be going through is how robots have really been used. What makes disasters so challenging that the legged robots and the advances are still lagging coming over here, as well as what really are the promising areas that will make a difference in complementing autonomy and morphology. And then what are the barriers to adoption? Going on a little bit, expanding on what we saw with Lee Bygrave's talk. So let's begin. Let's see, how have robots been used? So this is some highlights from the 31 disasters I've been to. The very first use of ground robots for the life-saving immediate response of a disaster was the World Trade Center in 2001. And you're seeing these different views of building collapses and things, and you see that small is better. You're trying to get into the rubble. But robotics, disaster robotics, isn't just ground robots. Marine robots are very important. And from those from the Brittany group, go marine robots, right? And so you see the ROVs. You see also that torpedo-shaped AUV. But you may not be aware of how much they were used to save 27 lives in the Syrian refugee crisis in Greece, because the lifeguards use robot boats to get things to victims. Drones are really the #1 type of robot used in disasters. It is almost every disaster since 2020 has had drones used in some form or another. But you think of them as getting their surveillance of that, but think about also they were used, most people don't realize they were used during the Fukushima Daiichi nuclear accident to go and look. And the video is it was downsampled for security reasons. But they also used for the Kilauea volcanic eruption, those little blinky lights are trees spontaneously combusting. But I think what's important is that now we're seeing is that it's not, the robots themselves are not particularly interesting. It's what can you do with the data? And you're starting to see AI, and I think we saw this a lot at the Champlain Towers, the big building collapse we had in Miami. So 280 missions, 3 to 5 times a day for 2 weeks while they were looking for survivors and then doing the recovery efforts. So being able to take drone data from drones that cost about $1,000 USD, US dollars, and being able to reconstruct 3D and then do these different types of maps and volumetrics. So we've got a lot going on. Now, as you saw that video, you might have noticed that nothing we were doing was replacing people. And it wasn't about climbing over rubble or working in intact structures or swimming in deep open water. And it wasn't about saving lives in the sense of running in and carrying someone out of a burning building. It was about helping responders do that. So I liken robots, no matter how autonomous or teleoperated they are, they're like fire trucks. They're tools. They extend the responders and the emergency managers. And it's not just the people on the ground. So I'll give you an example. So here's some footage. Hurricane Michael, a big hurricane that hit. The people on the ground, the tactical responders, you think of your fire department, your search and rescue teams, they're looking at that video and photographs from the drones that is far ahead of them, giving them the ability to see is anybody in trouble, how to get there, even if the roads may be damaged and they need to take a 2-hour route to get around, and what do they need to do to get supplies in. Meanwhile, people at the province, state, or federal level are looking and saying, okay, overall, how many people are affected? How long will they be affected? How will we rebuild this to get the services back? What will this mean? And especially, how much will it cost? Because these pockets of money for almost every country are in a special pocket of money that has to be activated with proof that you need that. So I like to reframe disaster robotics as a data to decision problem, that it's not about whether the rescue robot works, it's about whether the data gets from the robot to the right person in the right form, however they want to visualize it, at the right time for them to make the right decision that is going to save lives, that is going to accelerate economic recovery. So let's talk about why is that so hard, because there are so many brilliant robots, and we have seen such great work out in the demos and with the previous speakers. So what makes it challenging? Well, first off, disasters are different than routine emergencies. It seems like we have a lot of disasters in the world, but it turns out they're fairly rare and they don't occur in the same places. So they're unique. And they exceed, by definition, a disaster exceeds local resources. So it's not like a day-to-day emergency that you might have in New York City or in Paris, which they see everything, right, once a week. So for the rest of the world, these things are rare. And they also present different rules and regulations, different emergency waivers that you get, what you can do with robots and decisions. But for those of you who are into human-robot interaction or cognitive science, it also is different in terms of operation tempo. It's a very rapid pace. It's long shifts. The people have from people that are the search and rescue teams all the way up to the governor or prime minister, they are also with disruptive sleep, which doesn't help decision making. Additionally, everything has high consequences. Again, that adds more psychological impacts, and it's both off normal and that it is unusual for the robot to be doing this, slightly different, and it's an emergency, so that also increases the stress. Now, if you look at it computationally, a study led by the National Science Foundation and DARPA said there's really 4 things that make it computationally challenged. It's that extreme scale challenge, short time, covering a lot of space, many stakeholders, lots of data. It's interdependency. We heard the term wicked problem. It's a wicked problem. You solve it once, great. You're never going to solve that particular variation again. And the human system integration, I've already mentioned how tough that is on people. And we believe also what's unique is that it requires a different style of research, because you can't just fix a robot here. It's the whole system that you must integrate in. So what are the promising advances in AI and hardware? Well, autonomy is important, but it's not the big thing, and that's because autonomous navigation, obstacle avoidance in GPS-denied areas, in rubble, is really only part of the problem. I mean, what you're doing is you're trying to get through, as you can see at Surfside, spaces that at best are this big, and you're going down, around, in and out. It's wet. Everything you saw from Dr. Fallon's talk, only double it down in terms of complexity. So we've got that. And again, what do you do when you get there? What are you looking for? How are you seeing and understanding this deconstructed environment? Well, all right, legged robots are great, wonderful. I actually, soft robots, the vine robots, the snakes I really like. But I think that let's look at Spot. This is here at a building collapse in Fire Department of New York. Doesn't even make it in before it's fallen over. Now, eventually it did get up and keep going, but that's as easy as it's going to get. So we're really not trying to go over rubble. We're trying to go in these very small spaces deep within rubble. All right, so if those aren't it, if it's not morphology and autonomy, what are the big things? Well, I'm going to argue that there's 2 big things to work at that's really going to give us a big advantage, and that is human-robot interaction, and computer vision and machine learning. So let's see, well, why would I say human-robot interaction? Well, we talk about, remember, drones are the #1 type of robot used at disasters. Well, work that we've done with Dr. Ranjana Mehta and Camille Perez is that after 1 day of flying, the fatigue from flying a drone, even though it is autonomous, just you sitting there looking through the screen, has enough of an impact during a disaster to give you a blood alcohol equivalent of 0.05%. So for us in the United States that's legally drunk, it's also the max allowed for manned aviation, which is kind of interesting. You can fly unmanned systems, incapacitated, but you can't man systems. Yay. So we're working on the standards for that. And it turns out that Dr. Mehta has shown that it does not come back with a regular sleep schedule. So yeah, the first 2 days of disaster are always kind of very intense in there. But a good night's sleep doesn't solve. You feel a little better, but you never bounce back all the way. And so it's a continual degradation. Now, if we look on top of that, let's look at computer vision and machine learning. So drones are producing, since 2017, and we've been in 5 disasters, we're seeing about 64 gigabytes at least of raw imagery a day. And a lot of that drone imagery is going to be put into what these orthomosaic maps. And then somebody's going to look at them to say how many buildings are damaged, can we get there, are the roads open, how many people, those sorts of things, looking at that. So you imagine you're doing a lot of zooming and you're pretty darn tired, and that's a lot to go through. So they can't actually make it through all of that. Okay, so which just seems like a fantastic use of computer vision and machine learning, right, is to try to automate that or at least reduce how much they have to do by saying definitely nothing here, definitely something here, look at this and be sure. And so this is work being led by one of my graduate students, Tom Manzini, as well as Priya Parali and Reza Karnak. And so we just spread fairy dust. The only problem is that there is a lot to computer vision machine learning that we can't wave away. And one is that you have to have the annotated data sets. And then it's like annotated for what? We go to the responders, we go to the emergency managers. What do you want? We want building damage assessed. And what scale will we be using? Whatever works. Nope, wrong answer. Okay, you don't want me telling you what building damage. So we're looking at that. We'll see alignment in multi-view. Well, one of the biggest one, though, is, of course, in machine learning, is ever getting enough data in the data sets. And we certainly saw with Cyril's talk, Dr. Sacknett's talk about that as well. So last week, we released the largest annotated data set that we know of in the world. It has 10 disasters from 5 different types of disasters, hurricanes, tornadoes, a volcanic eruption that you saw, a building collapse. And also in terms of roads, since getting resources, rescuers and resources to the right places is important as knowing where to go, we have over 230, closely 230 kilometers of roads there. And how did we annotate that? We annotated it for building damage assessment. We're in the process of doing road damage assessment. So how did we do that? We did it with 151 students that we work with from 4 high schools in Texas and our partners up there through Carnegie Mellon in Pittsburgh through Pennsylvania. And of course we had to check and vet the data and stuff, but that turned out to work pretty well and got that done in a couple of months. And so this is an example of what it is, and yes, this is an atrocity in that I'm showing you results on our training data. This is just to help you see. So you see the roads here for the road damage assessment. The roads here are covered with water. They're annotated, showing red is bad, and then the model, if we give it to it, is actually showing water further down and stuff. So it's doing pretty well, and that's just your basic run-of-the-mill UNet. So we're very excited about that, and the building damage assessment basic models are very interesting as well. But again, we had a lot of work to do. Some of this is currently manual, alignment. Who knew GPS, according to GPS, isn't the same for maps, all different maps, and even drones, and even comparing satellite to drone imagery to map imagery. Everything is off, and for drones, it's non-linear. So you can't just bias it, figure out where it is, and move it up and over. So all of that's we're looking at learning, machine learning, to try to bring that in line. And also this idea of multi-view fusion. So you use drones when you don't have other information. Drones are great. They're like spotlights, maybe a few kilometers that they can cover. Think of a radius around you. Satellites, of course, can cover so much more. If you have weather, aviation, crewed aviation, higher altitude, Maxar is what our atmospheric or meteorological people use. If you have that data, it would be great. So part of what we're doing is trying to study and learn what's the difference. Can you use all or one, and can you get what is the quality? But you can see for damage of a building here, as you move up in altitude, you're clearly losing information that can be very valuable for damage. So we're looking at that, but it turns out the same problem of alignment, those of you who work in medical robotics know that people, their organs aren't in the same place exactly at the same time. And so these are very similar issues. But robots are being used, particularly drones. Like I said, almost every disaster you can look and see. And the recent bridge collapse in Baltimore had underwater robots there. It wasn't really publicized, but they were there. So why are you not seeing more of them? And so let's talk about those barriers. And for that, I'm going to use a case study from our study of how robots were used during the COVID pandemic. Now, during the first 2 years of the COVID pandemic, we were able to document 420 instances of robots being used in 53 countries. And this means that they were actually used in the field, in a hospital or a company or somewhere. It's not in the lab. You don't get, these were there. So that's a lot. And so what we see here is this curve. Well, that didn't show up, did it? All right, so imagine a curve to the, up and to the right. That's green, and that's superimposed over the pandemic curve, the epi curve of cycles, showing that as the time goes on over the 2 years, more robots keep getting used. But there's a sharp peak. They are initially heavily adopted at the very beginning. And there's another line that's very flat below, and that's a pink line that you can't see. Great. And what we see here, the top line, if we use the NASA Technical Readiness Assessment of Systems, not the maturity levels, you see that existing robots get used. If you could see this, you would believe that existing robots got used very quickly and continue to be used and adopted. And that makes sense. Things that already work and work for your application, you're just going to try to buy more of them, use them more frequently. We saw here, this thing, there's a curve that goes like this and then goes flat. So the first 3 months we were, oh, let's try this new thing that's never been done. Let's do that. And it was like, yeah, no one cares. Okay. And that leads to a model of, oh, look, that slide showed up. It leads to a model of innovation, of adoption that says, and this is consistent with other literature and adoption of things during a disaster, it's demand pull. It's what the responders want, not what we think will work. So it's not an innovation push, it's a demand pull. They know exactly a priori what their needs are, what their pain points are, what they would like technology to do. So you show it to them and they decide, first off, can I get it? Is it available? Is it suitable? Is there something that doesn't match that way that hospital works versus the way my hospital works? We saw this a lot with the disinfecting robots. And then what's the risk? What's the risk of something crazy happening? What's the risk of I need to hire another IT person to handle it? And if it all comes up well, existing robots are about 73% of the time. If you fit those, you will have a specific robot for that use case. Whereas you may very rarely, about 18% of the time, try something new. So you see that. So kind of a thing. So the barrier is that sometimes perhaps we aren't building the right things or we're getting it to them too late. we needed to get the technology before the disaster for them to accept it and experiment with it. But another thing I think that may be of interest to you that this study came up with, we looked at and noticed explicitly reported ethical concerns about the use of robots for COVID-19. And we found 61 of them. And no surprise, a lot of people were very worried about privacy. Drones were being used a lot for quarantine. Everybody hated that. I mean, everybody hated that. Okay, and there were concerns about job replacement, that these robots were going to replace workers in the factories and things like that. But here's some other ones that you may not have been aware of. The two-second next highest things were concerns about unproven claims of effectiveness. We were getting a lot of robots that were doing disinfectant and saying, yeah, I'm using the same light frequency as this other expensive robot, but I'm so much cheaper and I'm here. And besides the fact that you're violating intellectual property law and stuff. So they had that as a problem. You had all sorts of violations of regulations, people doing things. My favorite violation of regulation was somebody flew a drone around New York City, Central Park, yelling at people to put masks on, saying that they were from the police department. No, they were not. Okay. But we also heard concerns that there weren't enough regulations, that stuff was just being used willy-nilly. That may not have been true, but remember, these are public concerns, so it's how things appear to them. And then there was a lot of concern over unwarranted surveillance, that these drones and security robots were being used. But I thought it was interesting that in 5 cases, roboticists expressed concerns about the other robotic companies trying to use a disaster as a marketing tool, trying to overstate their claims, trying to do things. I thought that was an interesting thing. But if we look at that, I would say that these in blue, things that we'd like to stop, we would look at the governments stopping that through regulations or through laws or something, right? But roboticists, we can stop a lot of this ourselves. Certainly professional ethics in doing stuff, that's on us. We'll never be able to have a regulation that specifies exactly follow your professional ethics. That's part of us being professional, is to follow that. And so I think that's really important to keep in mind. A lot falls back on us. But let's go back to those expectations. So if you look at morphology, I mean, first off, ground, aerial, marine robots of all shapes and sizes have in fact been used since 2001, with the aerial robots, the small and expensive drones, dominating worldwide, including China, Europe, the US, since 2017. The morphology is a challenge, particularly if you're looking at building collapses and rubble. It needs to be smaller. But an even bigger challenge is data to decision. What are we doing with our sensors? How are we processing the data? How are we getting it to the right person in the right format for them to see what's going on, to have understanding? Computer vision, machine learning, the advances are mature. They are ready for transitioning, but with a lot of work with that that we need, because we have to have it to handle the data avalanche. Just too much data is coming in, but there's just a lot of work that has to be done. And the idea also is that human-robot interaction is very subtle, but it's very important on how we can interpret that data. But regulations and doctrine, no, they can't fix a lot of things. Government is important. They actually have a lot of relevant regulations, both about what to use and when to waive it. That's rational. But probably more important for us, the first easiest thing to do is for us to be more responsible about the way we innovate. But regardless, the takeaway, big takeaway here is that there's so much creativity, innovation, knowledge here. I hope we can work together on this. And if you have any interest in rescue robotics, using them for safety, security, any type of humanitarian applications, we have the big IEEE Safety, Security, and Rescue Robotics Conference will be in New York at the Fire Department of New York, and the call for papers will be out like at the end of this week. So I look forward to talking with you further about this.
Thank you, Robin. We have time for questions. Thank you for your presentation. What kind of disasters are taken into account into your data sets?
The disasters are hurricanes, tornadoes, a building collapse, volcanic eruption, and an earthquake. So I think that's nice. The other two drone data sets that are annotated are FloodNet and RescueNet. If you participate in any of those competitions, those are actually derived from two of the hurricanes in our data set.
I see you focus quite a lot on drones, and my question is, for example, can we use drones in terms, if it's a building collapses and we want to fly inside the building, for example. So how much drones are efficient when we need to explore narrow spaces?
Let me give you, bear with me, and let me give you a long explanation. Most of the time, we're not interested in intact structures where you would be able to fly a drone. If a person can get in there, the responders will do it themselves because they're things only a responder would know what to look for. When the Surfside condo collapsed, 12 stories collapsed at 1:30 in the morning, the Miami-Dade Fire Department was there. Half the building was still standing. They went in less than 15 minutes, visited all 12 floors, made sure everyone was out. Along the way, they were making sure that the elderly could get out, and that if you saw a bed with a lot of frills and pink gingham, that might be a child, somebody's grandchildren or may be there. And to look there and to go look in the closet because children are famous for hiding. Now, imagine what you're going to do with a drone. You can fly down the hall. Can you knock on the door? Can you open the door? Can you open the closet door? And so it's just, and do all 12 floors in 15 minutes. Well, maybe if we divide up, right? So Miami-Dade immediately used drones while the teams were going in the standing portion, immediately launched with the flashlight pack, their spotlight pack, and started scanning the rubble to see if there was what the state was and whether there were any survivors they could spot. So some things people are very good at, some things drones are very good at. Trying to duplicate, that's why I say they don't really replace them. They're doing different functions.
Okay, thank you for your answer.
So hello, thanks for the great talk. I was wondering if there is some connection. It's not really the same thing, like rescue robots is one thing and prevention is another. But I was wondering if, for example, the tools that are used for rescue robots could apply for prevention, like, for example, anticipating an eruption or considering if a building has some sign that could lead to a disaster, or like like the building could drop down or something like that. Like.
Great. What a wonderful question, and thank you, because yes, all of these things should be used not just after the disaster, but before. And that's another thing. A lot of these emergency management agencies, their public works divisions now have drones to look at roads, drainage, and land use. Wonderful for predicting flooding and what before and after with storms, to go ahead and prepare for those types of things. But also they already know the area, so they know where to fly, what's most vulnerable, what do we need to check on first. So we also know from cognitive psychology, people in a disaster, everything's going wrong. You're going to use what you're used to. If you're used to flying drones, You're used to your public works people, you're going to call them in and use that for that as well. So the more we see these used, the more they get used. And again, I think that explains in part why drones have become so dominant. You use them all the time. A ground robot, the bomb squads have ground robots, but they tend to be larger. Or they tend to be the ones you might throw in a building, but you can see those little throwable ones are not necessarily going to be able to get down into the rubble and around and through there in the wet. So, and they don't have, you know, the bomb squads often don't get used that often. They're always on standby. So they don't have that constant weekly experience. And I think that's been something that's held us back in the use of ground robots.
Thanks.
Thank you for the talk. You have been involved in several disasters. How do you capitalize on that? I mean, for the design of next generation robots, can we come up or translate this experience into benchmarks that have detailed operational scenario that can be reproduced in order to conduct research? That's question number one. Question number two, we expect with the global heating that we have more severe impact in terms of storms, tsunami, and whatever. Do you have any work in your lab predicting, analyzing what kind of new kind of disaster might come up with this global heating? Thanks.
The short answer is yes and no. So in terms of analysis, I have a bunch of charts I could show that probably wouldn't show up like my other figure. They'd be just totally blank. But the book Disaster Robotics goes through a lot of fundamental ways to ontologies and explains the different metrics for ground robots. Our publications since 2015 have concentrated on drones and what the metrics are for there, both for the performance, the weight, the logistics, user acceptance, and user interface. We have papers on where the operator errors are occurring and where things are breaking down in the data to decision. All of these should be fed back into the design, and we are working with some companies as advisors to have them add that into their packages. Now, in terms of predicting, we're not very good at predicting. No one is very good in the United States at predicting disasters. You know, like a hurricane, you know 2 days before about where to prepare. What we're focusing on is that if you are in a hurricane-prone place 2 days before, you know a hurricane may hit your area. Then use your drones to go ahead and map out and do the 3D elevation models so that you can use that to see which areas are going to flood. You're also going to, and this was done at Harvey, looking to see where there has been tremendous change in land use. Houston is a very large city that's growing rapidly. Certainly some of the cost of Harvey was because of land use where entire forests of trees had been cut down for suburbs. And that had not been updated to help figure out what the flow rates, the carrying capacity of the rivers in the area was and caused problems. So we say go, and Fort Bend was using our team to figure that out on the fly. In one case, they looked at one of these very, very large subdivisions and said, well, this subdivision's not going to get flooded because they've built levees. But they didn't follow the county guidelines, and all of the roads into that subdivision will be washed away if there's even a minor flood. Therefore, we are building an emergency road into that subdivision because the statistics are that at least 2 people will have heart attacks and need an ambulance within the first 3 days in any 3-day period. So you're going to have to get an ambulance in. And then they said, we don't even know how many people in the subdivision are pregnant and may need to go to the hospital. But we know just on heart numbers, 2 people. We can't get an ambulance in, therefore we are in 2 days building a ramp to get into that one. And so they were tagging all of those types of areas. By the way, as a follow-up to that story, They then used the drone evidence after they built the thing, after Harvey, to say, we are fining you for not being compliant with public safety. So there's lots of ways you can use it.
Hi, thank you for this great talk. Always great to see robotics research with feet on the ground. So I want to go back to the morphology question. Is there any useful morphology that can go into sort of dense rubble and be useful? Like, are there ground robots that are small enough or flexible enough that are not just in research labs but practically useful at this point?
Well, I think there's so much great work. You know, we're seeing soft robotics mature, right? And I think a lot of things are this close to being there, in part because of advances in the medical use of soft robots, because it turns out that sticking stuff in somebody's body, you've got the same sensor problems, you've got goop, you've got this, you've got to work with, you know, they're modeling close confined spaces. So we're really looking forward to both the snake-type robots, the smaller stakes, and the vine robots. Vine robots could be very good. Again, what we see, though, is not a focus on the types of sensing and information that the users would be using at the time. So anyway, so yes, we're close, but there.
Thank you very much, Robin.